Good morning to all of you. In previous session we have seen Z transform and some examples were solved where we identified the Z transform and the ROC of the obtained Z transform. Okay. In today's session we'll be discussing one of the property of Z transform, that is linearity property. Okay. So as we know that Z transform is a very powerful tool for the analysis of discrete time systems or discrete time signals, right? So the Z transform properties can also be used to analyze the given discrete time system or discrete time signals. Okay. So as per this linearity property, okay, so today we'll be discussing the linearity property and one example on this linearity property. So if x1 of n has the Z transform capital X1 of Z and x2 of n has the Z transform capital X2 of Z. So these x1 and x2, that is x1 of n and x2 of n, are the two discrete time signals. So x1 of n has the Z transform x1 of Z and x2 of n has the Z transform x2 of Z, right? Then the Z transform of linear combination of these two signals. Okay, so if I'm representing the linear combination of these signals as a1 x1 of n plus a2 x2 of n. Okay, so this is the linear combination of these two signals where this x1 of n has been weighed with a1 or multiplied with the constant a1, and x2 of n is multiplied with constant a2. Okay, so the Z transform of this linear combination of these signals will be a1 x1 of z plus a2 x2 of z, right? So this will be its Z transform. I can simply say that this as the signal x of n, and their Z transform linear combination Z transform is capital X of Z. Okay. So the linear combination of x1 of n and x2 of n has the Z transform of their respective Z transform linear combination, right? So where this a1 and a2 are the constants. So that means the Z transform of linear combination of signals, okay, that is x1 of n and x2 of n, we have taken its linear combination as a1 x1 of n plus a2 x2 of n. Okay, so the Z transform of a linear combination of the signals is same linear combination of their Z transform. Okay, so their respective Z transform was x1 of z and x2 of z, so we have taken the linear combination of their respective Z transform, right here. So let's try to solve one example by using this linearity property. So we can use all these properties, the properties of Z transform, to identify the Z transform of the given signals. Okay, so here we can apply the property of Z transform to solve or to identify the Z transform of given signals, right? So here is one example where we have to determine the Z transform and the ROC of the signal. Signal is given as x of n 3 into 2 raised to the power n minus 4 into 3 raised to the power n into u of n. Okay, so the given signal x of n is what is given as x of n is equals to, in square bracket, 3 into 2 raised to the power n minus 4 into 3 raised to the power n into u of n, or you can simply represent it as, I will multiply this u of n with each term here, so 3 2 raised to the power n into u of n minus 4 into 3 raised to the power n u of n, right? So as we have seen in the previous slide, we have taken here two different signals, that is x1 of n and x2 of n. Okay, so you can separate these given signal x of n, and you can represent it as considered as x1 of n. Okay, if x1 of n is equals to 2 raised to the power n u of n. Okay, and x2 of n, okay, and x2 of n is equals to 3 raised to the power n u of n, correct? So if we are separating this x of n into two different terms, so we are considering this as x1 of n, and this we are considering it as x2 of n. We can also directly identify the z transform of this given signal x of n, but we will try to identify the z transform of this x of n by using linearity property. Okay, we are interested in identifying the z transform of the given signal by using linearity property here, right? So this x1 of n and x2 of n were taken it from the given signal, right? So therefore x of n can be considered as what? 3 into x1 of n, right? That is 3 into this 2 raised to power n u of n minus 4 into x2 of n. Okay, so this will be your overall x of n, correct? So therefore these 3 and minus 4 are the values of constant a1 and a2, right? So your a1 will be 3 and a2 will be minus 4. Okay, so this z transform, if I'm taking the z transform of this x of n, so its z transform will be obviously x of z, and as per the linearity property, uh, the z transform of linear combination of this signal x1 of n and x2 of n will be simply 3 x1 of z minus 4 x2 of z. Okay, so moreover we are interested in identifying these z transform, that is x1 of z and x2 of z. So those two z transform will be identified from this x1 of n and x2 of n. Okay, so initially we'll try to identify the z transform of x1 of n, right? So the z transform of x1 of n, that is nothing but x1 of n, we have taken it as 2 raised to power n into u of n. Okay, so its z transform will be simply what? x1 of z, right? But this x1 of z will be equals to, as per the z transform formula, it will be summation n is equals to minus infinity to infinity, right? X of n into z to the power minus n. But here in place of x of n, here it is, the signal is x1 of n multiplied by z to the power minus n. So if I am trying to substitute the values of this x1 of n here, okay, the value of x1 of n is 2 raised to power n into u of n, okay, into z to the power minus n will be as it is. But we know that this u of n is the unit step sequence, so it will be 0 for negative values of n, so you can eliminate negative values of n from here. So instead of minus infinity to infinity, it will start for n greater than or equals to 0. So for n greater than or equals to 0, u of n is 1. So we'll take limit as n is equals to 0 to infinity. So 2 raised to the power n, in place of u of n, for these values u of n will be 1. Okay, so multiplied by z to the power minus n. So here you can take this n common, so it will be n is equals to 0 to infinity 2z inverse raised to the power n, right? So this will be your x1 of z, correct? This is your x1 of z. And if I want to simplify this geometric series we have seen in the previous session, so this geometric series can be replaced as 1 upon 1 minus 2z inverse, provided that 2z inverse is less than 1. Okay, so we can simply write it as x1 of z is equals to 1 upon 1 minus 2z inverse. Okay, but provided that this 2z inverse mod 2z inverse should be less than 1. So that means ROC for this x1 of z will be what? Mod z greater than 2, right? because if I'm sending this z inverse on right hand side, so it will be 1 upon z inverse. So if I'm taking it numerator, so it will be z. Okay, so 2 is less than z, that means mod z is greater than 2. Okay, so this is the z transform of x1 of z. Similarly, you can identify it for x2 of n. Okay, so we identified here the z transform of x1 of n, which is nothing but the x1 of z, and its ROC we identified here. Similarly, we can identify the z transform of x2 of n. Okay, so this the z transform of what, x2 of n we are identifying, like x2 of n, and x2 of n we have taken it here as 3 raised to power n u of n, right? So its z transform will be again x2 of z, it will be equals to summation n is equals to minus infinity to infinity x2 of n into z to the power minus n. Okay, so again in place of x2 of n I can substitute its value, right? So its value is 3 raised to the power n u of n, okay, into z to the power minus n. So again I can eliminate the negative values of n from the summation, because for negative values of n, u of n will be 0. So I'll start it from 0 to infinity. So this will be 3 raised to power n, u of n will be 1 for these values, into z to the power minus n. So simply I will take this n common. So n is equals to 0 to infinity 3z inverse raised to the power 3z inverse raised to the power n will be there, right? So this is your what, x2 of z. Okay, again by using this infinite geometric series you can simply represent it as 1 upon 1 minus 3z inverse. Okay, provided that this 3z inverse mod 3z inverse should be less than 1, so therefore its ROC will be mod z greater than 3. Okay, so we identified the z transforms of x1 of n and x2 of n, right? So as per this z transform equation, right, so we'll be simply writing the z transform of given signal x of n. This signal x of n is nothing but what, 3, what we have represented here it as 3 into x1 of n minus 4 into x2 of n, right? That is 3 into x1 of n minus 4 into x2 of n, right? But this signal basically x of n was given as 3 into, what was that, 2 raised to the power n u of n, right? 2 raised to the power n minus 4 into 3 raised to the power n whole into u of n. Okay, so this was the original signal. We represented as 3 into x1 of n minus 4 into x2 of n. This x1 of n is nothing but 2 raised to the power n u of n, and x2 of n is nothing but 3 raised to the power n u of n. So we are interested in identifying its z transform, and its z transform as per the linearity property is capital X of z, which is nothing but 3 x1 of z, right? That is nothing but is the transform of x1 of n minus 4 is a transform of x2 of n, that is nothing but x2 of z. So we can simply substitute these values here, that is x1 of z, we identified it as 1 upon 1 minus 2z inverse. Okay, so it will be simply 3 upon, so this 3 will be as it is 1 minus 2z inverse, right, minus, in place of x2 of z, 1 upon 1 minus 3z inverse. Okay, so 4 upon 1 minus 3z inverse. Okay, so the overall ROC, so this is the required z transform, that is x of z. Okay, for the given signal, the signal was given and its z transform will be 3 upon 1 minus 2z inverse minus 4 upon 1 minus 3z inverse. Okay, so this is the required z transform of given discrete time signal x of n. Okay, and its ROC will be, because for the first term ROC, as we have identified here, ROC is greater than 2, and for second term ROC is greater than 3, but we are taking the combination of it. So if you take the intersection of it, so the intersection of these two terms, that is mod z greater than 2 and mod z greater than 3, so the intersection will be simply, the overall ROC will be mod z greater than 3. So this is the required ROC. Even you can plot this ROC. So to plot this ROC, again you will plot it as what? On x-axis you will get real values of z, right? On y-axis you will get imaginary value of z. You will draw a circle with radius 3, right? And the ROC will be the exterior part of this circle. Okay, this will be the ROC. Okay. So this is how you can apply the linearity property. Okay, so as in linearity property, if two discrete time signals are given, it is x1 of n and x2 of n with their respective z transform at x1 of z and x2 of z. Okay, and if you are taking the linear combination of these given signal, that is a1 x1 of n plus a2 x2 of n, then its linear combination z transform will be simply the linear combination of their respective z transform, and its ROC will be the intersection of these two z transforms ROC, right? So I solved one example here by applying the linearity property. You can also directly identify the z transform of this given signal, but here we have applied the linearity property. So for applying the linearity property, we have separated out the given signal into two distinct signals, right? So this x of n, from this x of n we have taken two signal, that is x1 of n and x2 of n, as 2 raised to the power n into u of n and 3 raised to the power n into u of n. Okay, 3 raised to the power n into u of n. So the linear combination of these two signals can be represented as 3 into x1 of n minus 4 into x2 of n, because in this signal the values of a1 and a2 are, so a1 is 3 and a2 is minus 4. So we have taken the linear combination of these two signals, so the z transform will be the linear combination of their respective z transform. So x1 of n has z transform x1 of z, and x2 of n z transform can be represented as x2 of z. So we identified their respective z transform, that is x1 of z we identified, so x1 of z is 1 upon 1 minus 2 z inverse, and its ROC will be mod z greater than 2. Similarly, we identified the z transform of x2 of n, so it is x2 of z and it is 1 upon 1 minus 3 z inverse, and its ROC is mod z greater than 3. So we have combined these z transform to get its linear combination. So this is the overall z transform of the given signal x of n. Okay, and the ROC will be the intersection of these two ROC, so its intersection will be mod z greater than 3, and we have plotted it. So in next session we will see one more example on the linearity property. Okay, so thank you for joining this session.